Welcome to this introduction of the Coherence Go Client. My name is Tim Middleton. I'm a software engineer with the Coherence development team here at Oracle. The topics we'll be covering today, we'll give an overview of the client, we'll show you how to get started, we'll cover a few of the API features in a bit more detail and provide a demo. The Coherence Go client allows native Go applications to act as cache clients to a Coherence cluster using gRPC as the network transport. The client API fully supports Go generics and is available using Go 1.19 and above. It's supported with Community Editions 2206.4 and above and Commercial Editions with the feature pack 14.11 2206.4 and above. It brings the performance, scalability, reliability and availability of the Coherence data grid to Go applications. It provides the standard map-like APIs that you'll be familiar with, as well as cluster-side querying, aggregations, filtering of cache entries using many pre-configured filters and aggregators. It allows you to perform cluster-side in-place manipulation of cache entries using entry processes. You can register events to be notified of cache mutations such as insert, update, delete, and cache lifecycle events, as well as session events. There's support for Go primitives and structs as keys and values, and these are stored in the Coherence cluster using JSON by default, or they can actually be serialized to Java to support access from other Coherence language APIs. And as mentioned, we provide full support for Go generics in all of the Coherence APIs. So getting started, you'll need a gRPC proxy server running on your Coherence cluster. And you can actually use the Coherence CE Docker image to quickly get started. So in this example here, we're running the Coherence CE image. If we look at the logs, we can see that there's a gRPC proxy listening on 14.08, which is the default, and we can see there's a gRPC proxy server starting. In terms of Go, ensure you have 1.19 of Go installed and use the following go get command to get the latest version of the Go client, and you can import that into your Go program. So to get started, you first need to create a session. So you use the coherence.new session and you pass that a context. By default, it will connect to port 14.08 on the local host using SSL. You can use the following options to change that behavior. So you can use with plain text, you can use with address to specify a host port, or with scope to set the scope of the session. You can also set these via environment variables as well. So for example, to connect to my host on 14.08, you would use the following code. In the latest versions of Coherence, there are now two APIs you can access Coherence caches via. These are the named cache and named map. Named cache and named map are identical, except that the named cache provides the put with expiry function, allowing you to expire cache entries. If you don't wish to expire them, then just use the named map API. Both APIs fully support Go generics via the use of type parameters. So let's put it all together with a sample program. So we create the session, which is by default connecting to port 14.08, and this time we're using plain text. We defer the session close. We create a new named map with type int and value type of string. We put a new value in there. We retrieve the value for the key of 1. We update the key of 1 using put. Then we get the value again, and then we remove the entry. The following slide shows all of the APIs, and we'll go through these in a little bit more detail in further slides. But as a summary, we have the standard map-like APIs, the full generic support as we said, querying, aggregation, server-side processing, serialization, cache events, cache lifecycle and session lifecycle events, as well as infrastructure and load balancing. We fully support the standard map-like APIs that Coherence already provides in other languages. All APIs take type parameters for key and value for type safety. APIs that return values, such as get, remove, for example, they return pointers to the values to allow you to represent a nil value. This means you need to dereference the pointer to get the actual value. In this example, I'm putting a value of key 1 and the value of 1, get a value from the named map and dereference it. We should obviously check for a nil pointer here. We can put a value with expiry, so duration of 5 seconds, and get the size of the map, and we can also see if the map contains a value. Querying can be done by using keys using getAll, filters using entry set filter or values filter, or all entries using key set, entry set, or values. You can utilize various filters including comparison filters such as greater equal, slice based such as contains all or contains any or in, and logical filters such as and, or, and not. We use extractors to extract values from an object. Filters are applied on the server side, and keys, values, and entries are streamed back via channels. You can add indexes to improve query and aggregation performance. So we've got some examples here. We create an extractor on age, and we can get an entry set filter of all the people between the age of 17 and 21. Each of these channel entries have a key value and an error. So you must check the error to ensure that it's nil, and then that means you have a valid result. You can also then do a more complex one. We're going to retrieve the people between 17 and 25 who live in Perth or Melbourne. Once again, we check the error, and then we can also add an index on the age attribute. There's a full set of standard aggregators, including count, min, max, distinct, sum, average, and so on. You can do group by with filters for more complex aggregations. The count aggregator returns an int64 by default, and the average aggregator returns a big rat and must be converted to the expected type. The aggregators run in parallel on storage-enabled nodes, and the results are returned once this is completed. So a few examples here. We're going to get the distinct list of departments here. So we use a distinct aggregator, and we tell it what do we want to extract. We want to extract the department. We can get the count of all people. So we're going to aggregate across this named map and do a count. So it's the same as doing a size operation. We can also then do a count of all the people older than 19. So we have an age extractor again, and we run an aggregator with the filter. Age is greater than 19, and we do a count aggregator. We could then do the average age of people less than 30. And a bit more complex example, we will return the oldest person in each department. So we're going to use a group by, which says we want to group by department, and then we want to get the maximum age for each department. We also have the ability to run server-side processing using entry processes against a key, all entries, or a filter. So we have support for many standard processes, including increment, multiply, conditional, for example. And again, we retrieve the results via channel, which returns the keys that were updated. Using server-side processing is preferred than retrieving a value back from the cache, modifying it, then putting it back in. So in this example here, to update a person's age to 68, we invoke the processes.update, which takes the attribute and the value, and we invoke that against key 1. We're going to update all the people's age by 1 and return the keys that have been updated. So we're going to invoke all against all entries and increment the age. And again, we return a channel, so we need to validate that the error is nil. The third one, which is not really politically correct, we're going to update all people older than 67 and set them as retired. So we've got the age extractor, and we're using a filter this time. So we're saying where the age is greater than 67, we're going to update the retired field to be true, and that will return the keys of the people who have been updated. By default, the Coherence Go Client serializes any keys and values to JSON and then stores them in a JSON object in Coherence. This is usually sufficient for most applications where you're only accessing your data via the Go Client. If you wish to access your data via other clients such as Java, JavaScript, C++, .NET, for example, you need to use Java classes that are known to the Coherence server to represent the data model. To do this, we need to do the following. We define your data model on the server, configure JSON serialization, and annotate properties with JSON B property to match the Go struct. We create a file on the server called meta-inf type aliases.properties containing an alias and a fully qualified class name of the server. So customer equals com Oracle demo customer. You define your Go struct and you include a class attribute with the @class JSON representation. And then we create your object in Go, and you must set that class to match what the customer class is here. Once you put the entry in Coherence, it would then be stored as a custom object in the server, and then you could access from other clients. We also have extensive event features, so you can subscribe to cache events, insert, update or delete, and you can listen for all events, key-based events or filter-based. And you can expect the new and old values. You can also respond to cache lifecycle events to be notified when name maps or caches are truncated, released or destroyed, and there's also session lifecycle events. Just an example of a cache event here. So we've got a named map, and we're going to create a new map listener, and we're going to implement the onDeleted function where we get the key and the value and then just output it. We then add that listener to the named map and we defer removing it. So hopefully that gives you an overview of the API. Let's go and have a look at a demonstration. For the demonstration, we're going to run the Coherence to-do list example, which is a simple task management application written in multiple languages to showcase coherence. Firstly, we'll start the Docker image, which has the gRPC proxy enabled as well as the server-side configuration to serialize objects to Java on the server for cross-platform access. Let's look at the logs. So you can see we've got our gRPC proxy server running. Next, we'll run the JavaScript version, which uses React and uses the JavaScript client to access Coherence. So this is available on 17.02. Okay, so the task application here, and we'll run the Go example. So we'll build a binary. We'll show some code from the Go client shortly. And run it. It runs a CLI version, and finally we'll run the JavaFX client. So the JavaFX client will be using the plain old Java objects on the server. Okay, let me just rearrange these a little bit here. So the first thing we'll do is we'll add a task. So add mow the lawn. As soon as I add the task, we can see both of the other clients respond to that added task through map listeners and update their list. Then I can go into the React client here and get milk. And again, we'll see all the other clients get updated. We will walk the dog. And again, we see that updated. So now we say, okay, we've mowed the lawn, so we complete that one. And we'll see it's completed here and completed in the Go client as well. We'll completed getting the milk, and we can actually clear the ones that are completed. So clear command clears completed. I could click here, but let's use the Go client. Okay, so it clears the completed, and the only one's left is the one which is walk the dog. So let me let's do an update. Walk the dog after dinner. We'll add another one. Complete presentation. And then we will say from here we'll complete number 1, complete number 2. You can see they're all completed, and we'll now clear the completed tasks. So from this you can see that the information is being put in the Go client and the JavaScript client as JSON, and being serialized to JSON and being serialized to Java on the server. Let's have a quick look at some of the Golang code. So we have our command line which processes the commands that come in. So for example, when I add a task, I basically get the description and create a new task. If we look at the new task here, it sets the class to be task, which will match what's on the server and gives you the description and the created at, and it's completed to be false. Then we do a name map.put. If you want to delete, then we get the ID again and remove that entry. If you want to complete a command, what we do is we invoke an entry processor against that ID and we update the completed attribute to true. If you want to clear the completed tasks, we run an entry processor against all the tasks which are completed, so where the completed extractor is true, and we remove them. And again, where we update it, we run a update processor against that ID and change the description. Hope you've enjoyed this presentation today. If you'd like more information, please see the following links, which will also be put in the video description. Thank you.